Okay, I think everything's working. Is it working? Hello? Am I the only one here? I'm not the only one here, I know that much. Yes, we are starting soon. I'm still getting my few things together. I'm trying to get this worked out so that I can see both my chat and my notes at the same time before I even get going here, because if I don't have my notes, I'm going to end up rambling. More. I'm going to be rambling anyway. But while I'm getting everything ready, why don't we just cover a few basic things here, because this is the first time I've done this way. Actually, it's the first time I've covered this at all in this kind of format, because my direct messages are usually something more in the socio-political range, but I want to kind of broaden it a bit. I want to get out there and do more. And I figured I may as well go ahead and explain why I'm even doing this in the first place. This is something that I've actually kind of wanted to do for a long time now. And primarily, the reason why I'm doing this is because, and this is a bit of a story, I've always been a science nerd. Not exactly shocking, but I've always loved it. Even when I was in school, I tended to do my own research, and I would often come to my teachers with questions that were, well, I didn't understand it at the time, but they were far above the grade level. So I'm asking my high school teachers things that ended up being college level questions, and I didn't understand why they couldn't answer them. So they had to go and talk to like the college level teachers, say, I've got a student with this question. It's above my grade. I don't know it. Can you answer it? And so this led me to doing a lot of research on my own, because the adults around me just didn't have the answers that I was looking for. And they were, stupid things like saying, nuclear fusion. Why don't we have it? We have nuclear fission, which is where you take a uranium atom, break it, get energy. Why can't you just put it back together? I mean, anybody with a cursory knowledge of particle physics will be able to say, yeah, that's dumb, that doesn't work. But to actually sit down and explain it, that's a bit harder. In this case, a while back, well, actually, when I say a while back, I mean a couple of years back, I had actually joined a Facebook group. And I know, walking into a Facebook group and expecting any kind of intelligence is like going to the desert and looking for water. But I digress. I joined a group figuring that maybe if I surrounded myself with people that were also looking for answers... Okay, unicorn, we'll get to entropy. That's not this discussion, but we'll bring it up later. I figured if I surrounded myself with people who were also looking for the same answers, it would lead me to the answers that I was looking for. Because there are some things that that I still don't understand that I'm looking for, and I figured the best way to find those answers was to look where everybody else is looking. Anyway, I looked for these people. What I found instead, and before you say it, it wasn't stupid people. Okay? I didn't say there wasn't stupid people there, just that wasn't them. Also, I just noticed it still says starting soon. I'm started. Click. There we go. All right. What I did find was two kinds of people. I found two kinds of people. Number one were people that were much like me. They didn't know enough, and they were looking for answers, and they weren't finding them. The other kind of people were the people who thought they had all the answers, and were absolutely, provably wrong, and at the same time absolutely certain that they knew everything they were talking about. Now, sometimes this is not a bad thing. After all, we all make mistakes. We all think we know what the right thing is until we find out it's the wrong thing. I mean, once upon a time, when we were still hominids, that was, things like finding food. Hey, I found a plant. I bet we can eat this plant. Turns out it's poisonous. You're always right. Until you're wrong. The problem that I ran into is not only were some of these people, like, provably wrong, but they were actually so wrong that they were steering people away from the path. That they were steering people away from the path to finding answers. And when I say that, I mean, when we discuss things like quantum physics and quantum mechanics, these kind of things are almost entirely ethereal. There is nothing in quantum physics that you can pick up and hold, except for the Large Hadron Collider. Except you're not picking it up. You can hold it. You're not picking it up. But even then, you can go to the Large Hadron Collider. You can stand in front of that giant ring of magnets and say, "Look, there's the thing." But you're not actually holding anything that's related to particle physics or quantum physics. The things that we're discussing are so small, so insignificant. And when I do say insignificant, I do mean that literally. In the case of things like virtual particles, which exist for time periods that can only be measured on the Planck level. They are events that are so short they can literally be said to have never occurred at all. Not today's discussion, but we can get into that at another time. The point is that these things are so incomprehensible that it takes a certain kind of mind to really grasp them. And the unfortunate part is the same kind of mind that grasps the abstract concepts of quantum physics and particle mechanics. It's almost the same as taking something on the faith of God. You can't see God, okay? You can't touch God, you can't hold God, you cannot prove God. At the same time, you cannot touch a quark, you cannot hold a neutrino. I mean, these things are, as much as I know people are not going to want to agree with it, okay, I know this is literally just building up kindling between the church and the laboratory, but these concepts are very similar. And I'm going to leave it at that. Which is why I found out that when I joined a group for quantum physics and quantum mechanics, it ended up with metaphysics. And metaphysics, if you're not familiar with it, is basically the bridge between spirituality and science. And it's almost all bullshit. Quantum mechanics is not a path to enlightenment. And JP, we cannot see or touch them. We can measure some of them. However, when it comes to things like neutrinos literally do not interact with matter. That is one of their basic properties. We can theorize how many of them there are. And we believe we know how many of them are passing through a particular cube of matter at any given time. But because they don't really interact with matter, that also means that they don't interact with the matter that makes up our instruments. Again, another subject for another time. And because of people like Feynman, we actually can prove the existence of quarks and such, but we still never directly observed a quark. We can't separate a quark from, say, a proton. We do have some stuff going on with places like the Large Hadron Collider and other particle colliders out there where we can smash two particles together, usually protons from hydrogen, and we can see all the things shooting off. We can look at these and say, we believe that's a quark. We believe that because all the previous data has led us to believe that that's a quark. Is it a solid proof? I would argue it. It's good proof, not necessarily concrete, in my opinion. And I'm sure that there's going to be a lot of people out there that are going to disagree with that opinion. And that's fine. People are welcome to disagree. We can have that discussion. Anyway, getting back on track. I found out that there was a lot of metaphysics and stuff out there, and metaphysics is just a great way to take a scientific investigation and just flush it straight down. Because if you're going to take a discussion about quantum mechanics, vacuum fluctuations, you want to talk about energy fields, and then you want to introduce this into the idea of how electromagnetism generated by something can also interact with the energy fields inside of the human body and how that aligns with certain chakras and allows you to project your consciousness somewhere else using quantum now we've completely crossed the line, okay? We are no longer in the realm of any kind of grounded science. And so I found a lot of that in there. That's also one of the reasons why that group eventually dissolved. Eventually there was like nothing left of any substance and people just gave up. So that is one problem that I ran into. And that problem is actually really easy to solve. Get those people out of here. No more of that. Unicorn. Theories and laws are always tested over and over. Every day we test the law of gravity, but if one day we start floating away, then it will no longer be a law. That is true. And that is true of all laws. Not just laws of physics, but even laws of government. Because even those laws are tested over and over again. And they're laws until they're not. However, that was a different direct message. Go watch the first direct message I ever did on law. It's worth it. Okay, so now that we've got that done, metaphysics out, okay? Those people, gone. We're getting rid of them. The next thing was, some people have very basic questions, okay? And they are basic questions like, why can we not travel faster than the speed of light? Okay? And if you ask that question in any kind of open forum, I can guarantee that if there are 60 people in that room, you will get 60 different explanations as to why you cannot travel faster than light. Why? Okay? Now, you can go ahead and you can bring up all kinds of different equations, and you can explain them in painstaking detail. And you can do it in 60 different ways. And at the end of the day, what have you accomplished? You have accomplished nothing. Because the person is, number one, going to be completely overwhelmed because you're throwing calculus and differential equations at them. And they're not going to comprehend any of the numbers at all. This will make no more sense to them than showing a math book to a monkey. Okay? It's not going to work. And secondly, even if you get a dozen people that might all be correct about it, if they all explain it in a different way, trying to put their own spin on it or trying to make sure that they're accurate about different things, then at the end of the day, this person has to comprehend 12 different explanations of the same thing, and they're not going to understand any of it. I know this because I saw it. I saw it repeatedly. And generally speaking, it was always greatly overcomplicated in the first place. Half of the reason why I do these direct messages is because if you go and watch the news or you do research on the internet, you can find extremely detailed information on just about anything that you want to see. However, finding that information in a form that is digestible and understandable by the average person is difficult to get a hold of. Even if you go onto YouTube, onto channels like Minute Physics and things like that, even they can get a little technical sometimes and have you go back and watch it several times before you can really understand it. There are some things where that's unavoidable. I mean, if you want to start talking about, what would be a good example of this? If you want to start talking about thermodynamics, there's almost no way you can get into a discussion of thermodynamics and not get into numbers. It's almost impossible. You can get into a very cursory look at it, but sooner or later you're going to have to start talking equations. So what I like to do, and what I tend to be really good at, is taking these concepts and boiling them down into something that is digestible, understandable, and we can get everybody on the same page. And then, if you want to go further on your own, you can do that. But if you have any kind of misconceptions or misunderstandings, I want to be the person who can say, let me simplify this for you so that you can understand it. And that brings me into today's discussion on wave-particle duality, because this is one that I had to explain several times over and over and over again. Hell would technically be exothermic, and that's because it produces its own heat. There you go. I just made it easy for you. If hell was absorbing heat, it would be endothermic. But hell is producing heat. There's all kinds of fire and brimstone down there. It is radiating with heat. The question now is hell in the middle of the sun? Because, I mean, there is no hotter place than the middle of the sun. Except potentially the middle of a black hole, but we can't prove that yet. Okay, so, let's get started today, and hope that my notes are sufficient, because I have done this discussion several times already, and I haven't been satisfied with it any time. And I've ended up deleting it, and that's why I'm doing it live now, because now I can't delete it. Ha ha ha! I tricked me. So, wave-particle duality. This is one that I had to discuss several times with people, because when somebody will mention wave-particle duality, they will usually do it in the following way. They will say that a particle, like a photon, like an electron, basically anything in your lepton group, is both a wave and a particle at the same time. And this is impossible. How can something be two things at once? Well, actually, Schrödinger has a good idea, but we'll get to that later. The fact is that particles are not particles and waves at the same time. They're not, okay? I want to make this very clear right out the gate. A particle is a particle, and that's all it is. So if you're trying to bridge this mental image you have saying, I have a particle, but now it looks like a wave, but now it's a particle. Nope, it's just a particle. It is a single point of energy, basically. I mean, that's all that leptons are. They are just a single packet of energy. So right out the gate, we have simplified a ton of this. Particles are particles. So where does the wave come in? Here's where the wave comes in. Wave-particle duality is not a description of the particle itself, but instead it is properties of the particle. Now when I say that, let's look at the properties of a particle and properties of a wave. The properties of a particle is that it is a singular entity, okay? It is a singular packet of something. And I can make this simple for you because a particle of light, a particle of energy in the electromagnetic spectrum, is a photon. Okay, we all understand photons. But I mean, we work with particles all the time. Dust is a particle. Sand is a particle. We have particles around us that we interact with daily. Now, granted, these are on a much larger scale than photons, but you understand the concept. It's just a singular instance of something. Now, if you take a whole bunch of sand and crush it together, you could get a rock. But at the same time, you could take a rock and grind it down into sand. So you have sand makes up rock. Photons make up light. Pretty simple, right? You could take light and through prisms and through filters and everything else, you could actually filter out a lot of that to separate a single stream of photons if you had good enough materials and good enough equipment. I mean, this is kind of where lasers come in, but we've done things like this before. So right out the gate, now you understand particles. Super simple, you get that. Waves. Now, what is a wave? A wave is less of a thing and more of a behavior. So the property of waves is that they are a transfer of energy. You think of waves and you think of you think of like the ocean. And you think of waves that travel across the ocean. You see the wave coming from over there, and it comes past you, and then it continues off into the horizon, and you lose track of it. You think of that shape as a wave. The fact is that the shape isn't really the wave. It's a behavior. If you could look at a wave on the ocean down to the actual molecules of the water, what you would generally find, and there are other animations out there, I should have had one pulled up, but I don't have a lot of animations to show off. What you would find is that the actual molecules in the water don't really move. What instead is happening is the energy in the wave is being transferred from molecule to molecule to molecule as it just moves through. And it's this behavior of moving through things that is a wave. So when we talk about wave-particle duality, we're talking about yeah, actually right there. A wave is as the behavior at a baseball game. That's not a bad example. No person is moving over a seat, but the wave still continues on. That's a good example. So you have this behavior of the energy moving through these things, and that's a wave. So, wave-particle duality. What do we mean by this? When we talk about wave-particle duality, we're talking about the behavior of particles to first off be particles, but as they're traveling to behave like waves. And that is that when they move, they will interact with other things, they will transfer energy, and the way that they transfer energy is not necessarily always linear. After all, two molecules of water may not bump into the same two molecules at the same time. They're kind of wavy. They occupy an area. And that's getting into something that we'll get to in just a minute. But this is a particle, and it is acting like a wave. So it has both of those behaviors. Now, when you talk about wave-particle duality, one of the things that people will bring up a lot is something called the double-slit experiment. And I wonder if I can just bring up a picture of that real quick. Double-slit experiment. Now, this is a very famous experiment that's gone back a very long time. Everybody has seen this picture. And click the button. Why is that not working? Is it working? I don't think it's working. Ah, see, here's the technical difficulties. I knew that we'd have them. There we go. Okay. I knew I'd get it eventually. Okay. So, here's a double slit experiment. I don't want your other picture, I just want this one. So the idea of the double slit experiment is this. If you were to just shine a source of light at a plate with two slits in it, what would most normal people expect? Most normal people would say, I've got two slits, I'm going to get two holes. Okay? But that's not actually the case. What we usually get is this kind of pattern right here. And a lot of people say, look, this is a demonstration of particle mechanics and the wave-particle duality. Look, it's right here. And they say, here's the proof, but they never actually explain it. Probably because they don't actually understand it themselves. So I'm going to try and explain that right now. And I think they're going into that right here. So this is probably a really good website to go to if you want a further explanation. But to make this really simple, what they're showing right here are these waves. And when they're showing these waves, they're showing them as a single solid object. So it hits here, and then what? Well, I guess it goes through here, and what little gets through here, oh, look at that. It's another solid object. How are you getting this pattern from this wave? Shouldn't this wave be hitting the entire thing back here? Well, obviously this is just a diagram, but the problem is that our understanding has to be built on these models. And so if the model is bad, and this is undoubtedly bad if you don't know what you're looking at, then you cannot comprehend what you're looking at. It's that simple. So if we could simplify this in a different way, how about this? Now I did come prepared for this. Welcome to Paint, because I don't have any kind of drawing skills or anything like that. This is just MS Paint, but I'm going to use it for my purposes. So this should be lines, right? That's right, it's art class with Cat. So the first things first, I want a big old dot. So brush, marker, size, big. So here's our, go, do it, do the thing. Oh, okay, never mind, undo that. So, come on. Okay, there's our point of light. Okay, good enough, whatever, I don't care, it's good enough. Maybe marker was a bad choice. I have no idea. Just brush, I guess. Good enough, whatever. Alright, so there's our source. Now, obviously now we need to have two slits. So, here's the middle one. Here's the top one. Here's the bottom one. And then, of course, we have our collector in the back. Yes, we are going to draw happy little particles. Okay, now, when you looked at the other image, you saw the waves that were coming in. But instead of looking at those waves of particles coming in, we're going to look at a particle, okay? We're going to take this guy right here, okay? He's going to come from our light source right through here, and he's going to land Well, actually, you know what? I'm going to do this in different color. Different color. We'll do red, okay? So this guy's going to come through here, and he's going to land right there in the collector plate. Isn't that great? Isn't he happy right there? Okay? Same thing's going to happen over here. We start from our light source. Nope, you stay there. We start from our light source, we come through here, right there. Okay? So, one single particle right through the holes. Now, what about this particle right here? Come on, stop it. That comes over here and hits the edge of this. Okay? So he's going to hit right there on the edge. Well, then he's going to have to, deflect. It'll impart a little bit of energy into the material, and then it'll deflect back here. Just like that. What about this one that comes over here and hits here? Just like the other one, it'll hit, it'll interact, it'll deflect, it'll come back right there. Okay? So as we can see, we already have a pattern going here. Now what about this one that hits here at a little bit shallower of an angle? It hits, and then it comes right there. And actually, Unicorn, it will absorb and deflect. Because photons, which are just electromagnetic energy, they are just a massless packet of energy. When they interact with an atom, when they strike the atom, they get absorbed, usually by the electrons inside of the electron field. This is what causes electrons to jump orbits. If you've ever seen the model of an atom, you'll see that it's got your nucleus, and it's got a ring, and a ring, and a ring, and a ring. Those rings can only contain a certain amount of energy. If you add energy to the electrons there, the electrons will jump to a higher orbital sphere. However, if the sphere is unstable, they will actually fall back down to the previous sphere where they originally were, and they'll release the photon with just a little bit less energy. Think of it as getting just a little bit dimmer every time it interacts with something. That's why every time you shine light through a pane of glass, it gets a little bit dimmer. You can't notice it in just one window, usually. But if you stack up a whole bunch of windows and shine a flashlight through 10 of them, by the time you get through 10, there's not a lot of light left. The windows might also have been tinted a little bit, but regardless, that just makes it more dramatic. The fact is, you stack up enough clear glass, and you will stop light. And I mean, we do have examples of that. Go to the ocean. You can pick up a glass of water out of the ocean, and it looks clear. Go diving in the ocean, and you get down like 50 feet, and it's already getting dark. There you go. Anyway, back to the model. So, we've already got 5 particles out here, and we can see that they're already deflecting in different ways. This guy's coming in about the same way, so he's going to land in roughly the same place. This one's coming in really shallow, and so it's going to hit here, but when it deflects, it's going to go over here. Hello, Tux. Yes, this is different. We're discussing particle physics today. Now, here's the interesting thing. If I were to sit here and do this 10 million more times, drawing the path of every single particle, what would it look like by the time I got done? The answer is you would not end up with these curvy waves. You would not end up with this coming out of here. You would end up with a cone of particle rays that were coming through here. But once you got to the back plate, once you got back here, you would end up with this. You would see this interference pattern on the back. And this is what clued people into the idea that perhaps you can have particle and waves at the same time. They are particles. If you were to take this gap out, then they would just continue to stream forward like particles. But this is the same interference pattern you would see if you did it with sound. If you were to fill this area with water, and then you would go ahead and just either drop a stone in, or you would put in like an ultrasonic metal rod or something like that to generate the waves. This is the same interference pattern you would get. Now, the water's not really moving, just like the wave on the ocean. But the energy moving through it would look exactly like this. And yes, unicorn. When we're talking about light, whether it is infrared light, visible light, ultraviolet light, even going all the way down to microwaves and radio waves, we think of it in characteristics of it being different, but it's not. A red light photon is no different than a gamma ray photon. Photons are photons. The difference is how much energy the photon has. It's still a single packet of energy, but the more intense the energy, the higher the frequency. And there you go. Red light is the lowest frequency light of the physical light that we can see. We can't see anything lower than that. Same with violet. We can't see anything above violet light. And hello, Jeffrey. Violet light has higher energy, and if we continue to add energy to a source of light, eventually that violet light would go to ultraviolet, and it would go beyond our ability to see it. The same thing happens if we continue to remove energy from a system. And to make this really easy for you to understand, picture something hot, like a red iron bar. All right? Go to like a forge or a blacksmith or something like that. See them pull out that piece of iron. Now, generally speaking, when they pull that iron straight out of the fire, it's probably going to be white hot. All right? It is a very hot piece of metal. Do not touch it. Do not taste it. Don't even think about it. It's very hot. But what happens? Well, that white eventually turns to yellow as it cools. Why? Because it is so hot, and the atoms in the metal are so unstable now, which is what allows them to forge it, that it is shedding energy like crazy. Partially because the atoms are unstable, partially because of entropy and thermodynamics. Do not lick the forbidden metal. Don't do it. But at any rate, that metal is going to radiate that energy away. And it is just energy. We call it heat, but heat is just energy. It's going to radiate that energy away, and we're going to feel it in heat. We're going to see it in light. And the fact that we can feel it is your clue. Actually, Tux, you're not far off on that one. Anyway, you can see the iron bar as it's hot, but as it cools, the white turns to yellow, the yellow turns to orange, the orange turns to red. and it's getting cooler and cooler and cooler. It has less and less energy. However, very importantly, red is the lowest energy level that we can see. But if you had a thermal camera on it, you would see that long after it leaves the energy level that we can see it, when it's no longer red hot, it's just hot, it is still giving off massive amounts of energy in the form of infrared. And if you continue to watch it, it will continue to grow darker and darker and darker in the infrared spectrum. But if we had something that could see microwaves, or if we could visualize radio waves, you would still be able to see those as it continues to lose energy until finally it loses all of its excess energy. It comes into equilibrium with its environment, and it's then just a lump of iron. Bit of a tangent there, but yes, that is why red light tends to get filtered out before everything else. That's also why if you look up at the sky is blue. Our atmosphere is, I think they all kind of agree that the atmosphere is just like 100, what is it? I don't remember now. It's like a 100,000 or 1,000,000 kilometers in thickness. I forget. But anyway, all the light from the sun has to go through all of that. It's got to go through the ozone layer, it's got to get through the stratosphere, the ionosphere, the troposphere before it gets to us. And all those lower wavelengths, they all get filtered out along the way. So by and large, when you look up at the sky, the majority of light that's left that's actually reaching you is blue, which is one of the higher energy wavelengths. So there you go. You got 2 more answers today that you probably weren't looking for. Just a font of information today. Anyway, getting back to the subject at hand. Yes, that is exactly how radioactivity works. Except it's a little bit different. It's not necessarily excess energy, it's beta decay. Totally different subject, not getting into it now. So anyway, double slit experiment. I think we've got this one. I absolutely don't believe you, Tux. You will not let me do my things. However, I can appreciate the fact that you're a liar. You do you. Alright. What's next on the list? Let's see. According to this, next on the list was the Schrödinger equations. We're skipping that because they're very complicated, and I don't think they're all that relevant. Jeffrey, if we had an even thicker atmosphere, then yes, the sky would probably be a bit more violet in color, and maybe a little bit darker. However, interestingly enough, if we had less of an atmosphere, it would probably be a bit more into the green spectrum, but also a lot brighter, meaning that it might look a little bit more green, but it might also look a little bit more white, just because there'd be more energy coming through. You would never really get a red sky. I mean, we sometimes get red skies, but that's only when it's being filtered through like a ton of... we do get red skies, but that's only when they've been... the photons have interacted with a lot of our atmosphere. Like, for example, sunrise, sunset. We see red, orange, yellow, all those colors all the time. However, the light that we are getting during sunrise and sunset isn't necessarily red light from the sun. Rather, what we are seeing is that same blue light that we're used to. Well, the same blue, violet, white light. It's the same light that always gets through. But, and if you've ever worked in technology with things like wireless services, you'll understand this concept. The light that's getting to you isn't really different, and it's the same photons that have been getting through the atmosphere normally. The difference is that they're not coming straight down through the atmosphere like they do at noon. They're coming across the entire horizon to reach you. Light can only travel in a straight line unless you're talking about extreme gravity wells, and we're not getting into that right now. So the light is coming to you straight from the sun. Now, that means that it has to pass through 1,000,000 kilometers of atmosphere or 10 million kilometers of atmosphere. It's the same light going the same distance. By the time it gets to you from the horizon, it will have lost more energy, and it'll look like a lower frequency of light, because it is a lower frequency of light. There's other examples of this kind of thing as well. One of my favorite is... Actually, no, I'm not getting into this. This is a distraction. It's a tangent. Not doing it. Anyway, what are we getting into next? Let's see. Next was Schrödinger. Skipping Schrödinger. Okay. No, wait. I do have to get into Schrödinger. Never mind. We have to do this. I'll make this very quick and very simple. Erwin Schrödinger. Most people know him as the guy that did Schrödinger's cat. However, most people don't understand Schrödinger's cat. And by the time that Erwin Schrödinger died, he hated Schrödinger's cat. Mostly because nobody understood it. But you have to understand that Schrödinger was doing his work at the same time as Feynman and Heisenberg and Einstein and all of them. So when he was developing a lot of these theories, he was pretty much surrounded by people that were the apex of the science community. These people really did not know how to talk to the average common person. When Schrödinger developed his equations, he kept struggling with a certain concept, and that was that the more times he ran the equations, he kept coming up with different answers. Okay? He eventually did manage to nail them down. However, he found inaccuracies in all of his equations. He could calculate them down to a certain point, and after that, it became difficult to get exact. And so what happened was, he determined that there was a certain level of uncertainty, and we're going to come back to that, when you got down to a certain level of particle mechanics. He was never really able to grasp it or explain it. I mean, he didn't have the time to work it out. But what he came up with when he tried to explain it was Schrödinger's cat. Now, everybody, I'm pretty sure, has heard of Schrödinger's cat. The idea is this. You put a cat in a box, which is not hard because cats love boxes. Inside of there, you put a vial with radioactive cesium, okay? And then you put a timer with a hammer set to a completely random number that nobody knows. At some point, well, okay, then you close the box. At some point, that timer is going to go off. You don't know when. It's going to break the vial. It will release the cesium. It will irradiate the cat. The cat is going to die of severe radiation poisoning shortly. Now, answer the question. Is the cat alive or dead? You can't open the box. The obvious answer here is, I don't know. You can't know. Without some kind of information input, you'll never be able to know whether the cat is alive or dead. If you can't see the cat, hear the cat, feel the cat, you have nothing to go on. You don't know. Most people simply take that as an explanation of, okay, so, I mean, it can't be both, can it? I mean, obviously it's either alive or dead. And for the average person, that's right. But we're not dealing with a physical model, okay? We're not dealing with an actual box, an actual cat. This is an abstract theoretical model. And yes, Tuxedo, science killed me. But am I really dead? The point that Schrödinger was trying to get to is the fact that he didn't know. And so when he was developing his equations, he said that we'll simply take what we do know, and we're going to assume that every possibility is true at once. Okay? If we're trying to measure the properties of a particle in motion, or trying to measure its location, why don't we just assume that everything is true? Okay? And in a certain respect, he was right. And we know that he was right about this because Heisenberg, I forget what his first name. What was his first name? I feel bad. I feel like it starts with an H. Nope, it doesn't. Werner Heisenberg. I'm bad. He's a German physicist. I'm German. How do I not know this? Anyway, Werner Heisenberg kind of expanded on what Schrödinger had started. Now, most people have probably heard in passing of the Heisenberg uncertainty principle. More people have heard about Heisenberg, the meth dealer. He's not involved in this. So don't even think about it. Don't do it. Okay? Wrong Heisenberg. We're talking about the physicist. Now, Heisenberg came up with the uncertainty model, and he started with the Schrödinger equations and said, I think I found the problem. The uncertainty principle is a very complex equation filled with many numbers and letters and symbols that I could not identify with a gun to my head. But I can make it very simple. Heisenberg's uncertainty principle says this. When it comes to particles, we can know where the particle is, or we can know where it's going and how fast it's going. But we can't measure both. And the fact of the matter is that if you tried to measure both, you would lose one or the other. In order to find out where the particle is, you have to stop the particle. The minute you stop the particle, you no longer have its speed and vector. You no longer have its velocity. At the same time, though, you can actually track the velocity of a particle. We've done it. But the problem is that when you're talking about photons and electrons and things like that, they travel at the speed of light. That is a really big number. That's this big a number. That's a big number. And that's in meters per second. Okay? Why don't we Americanize this? Miles per hour. You see that number? That is 6.706 plus 8 more zeros on the end of it. That's a big number. Okay? The speed of light is unfathomable. So we can get the velocity of a particle, or we can get its location, but we can't get both. You just can't. Not with the tools that we have now. And a lot of this, I will admit, does fall down to the fact that we don't have the tools we need yet. And I'll get into another discussion about that later. Because a lot of people have complained that, you know, we can't travel faster than the speed of light. Nothing travels faster than the speed of light. And it's, well, okay, nothing that we know of. But everything that we have measures light. Light are photons, which are particles of electromagnetic energy. Whether that's infrared, visible, ultraviolet, X-ray, or gamma. All of our telescopes see light. None of our telescopes see not light. So how could we ever see something that travels faster than light with a telescope that doesn't see not light? Sooner or later, we will have better equipment and we will be able to better measure these things. But that's a bit of a tangent. So Heisenberg said we can know one or the other, but we can't know both. And that was a very good place to be, because now we know we can't get both. But what we can do is we can measure it twice. If we have two electrons, we can measure the position of this one, we can measure the velocity of that one, put it together, and you have the information we want. So great! Heisenberg has cleared it up. It's not that Schrödinger was wrong, it's just that Schrödinger wasn't quite doing enough yet. And that's kind of a really abstract concept, really, because it's like, okay, but, I mean, who can even picture an electron? Here's a better example for you, okay? I want you to picture a bullet, okay? We are all familiar with guns. Everybody in the world is familiar with guns. Whether you live in America and you have an entire arsenal of your own, or you live in the backwoods of Malaysia somewhere and all you have is an old musket that you used to hunt whatever it is that they hunt in Malaysia. I don't know. Flamingos? At any rate, we're all familiar with bullets. You can sit here and you can watch a gun be fired, okay? So, pull the trigger, bullet goes pew, out the end. How fast was that bullet going? And more to the point, where is it at any given point of time? Now, if you put in one of those little, whatever they are, the little meter thing with the two sticks that come up that measure the speed of things, you can shoot the bullet through those and it'll give you a measurement of just how fast the bullet was going. And that's great. And if you ask somebody who's taking the measurement on speed, where's the bullet, they're going to say, I don't know, over there somewhere. Okay. At the same time, though, you can get a high shutter rate camera. Okay? Park it right there next to the gun, and as soon as you pull the trigger, it'll go off as soon as that bullet comes out of the gun. Right there, for all posterity, you can see the bullet right there. Crystal clear. How fast was it going, though? You can get one or the other. But you can't have both. The same concept is true with photons. The same thing is true with electrons. You can get one or the other. Just like we can't measure everything about a bullet one time. We can actually do it with a bullet, but it's a much easier example. I also like to compare it to a truck going like 1,000 miles down the road. You can either measure how fast the truck is going, or you can read whatever's painted on the side of it. But you can't read it while it's going that speed. So that gives you a good example of the Schrödinger equations, Heisenberg's uncertainty principle, the idea that we can only know so much about the particle at any given time. Now, why is this important when it comes to wave-particle duality? I know, feels like we're kind of wandering off into the woods here, but, this This is where I'm going to bring it all back, okay? So, here we go. I'm going to come back to Paint, the lovely, lovely MS Paint, because this is the best tool I have. It's sad that this is the best tool I have. Okay. We're going to first delete this. Deleted. I know, it was beautiful, but we're not going to. So, what we have is, or what we're going to have here is a particle, okay? So, particle. That's actually really small. I can't see that. Let's make it bigger. There we go, particle. Okay? That's a photon. Now, when the photon is sitting still, we can say, there it is. Okay? It's right there. Now, what happens when we accelerate this photon to light speed? Okay? We have no idea where it's going to be, because as we just established, we can know where it is, or we can know how fast it's going, its velocity, but we can't know both. So we know what the particle is, and here's the particle part of the duality. Where does the wave part come in? Okay? Now, whenever you've seen a picture of a wave, they usually show you a sine wave, which is horribly drawn like this. And they say, that's a wave. I take it back. That's a beautiful wave. That is the best wave. And they say, and this is why most people get confused. This is why at the very beginning I said, stop thinking of it as both a particle and a wave. This is not a photon. This is just the behavior of it. And when I say this is the behavior of it, think of this not in terms of this giant wave here. Instead, think of this. Okay? Just think of this. Now, what does this look like to most people? Most people say that's a hump, or it's a bump, or it's a hill, or something like that. However, if there's any statisticians in the audience, what does that look like to you? It kind of looks like a bell curve. What is a bell curve? Well, a bell curve is a tool in statistics used to explain probabilities. Generally speaking, your highest probabilities are going to be here in the middle, because it's the highest point, and then the probabilities or averages or whatever else will fall off more to the wayside until you get to the ends where the probability of something happening is basically 0. Now, why do I bring this up? Because this is where the wave comes in. We have our little bell curve here. What happens if I continue it just a little bit? Okay. Now we have the same bell curve, but it's upside down. And if I keep going, we have a sine wave. Okay? So our particle is going to be behaving like a wave. It'll have probabilities, because of Schrödinger and Heisenberg, of being anywhere inside of here at any given time. Now, if I were to take my little photon and just shoot it through here, that's awful. Why am I using this tool? I want a straight line. I have a straight line tool. There we go. So if there's the course of my particle, I can see that my probabilities of it being in any certain place do intersect at certain places. It has definite positions. We might not know them, but we can guess. We can calculate them. We can make theoretical models about it. But more accurately, we could also just take this line and instead put one line up here and one line down here and say that our particle can be anywhere in here at any given time we're measuring it. We've got the velocity, and we can simply make the assumption, as per Schrödinger and as per Heisenberg, that our particle is in here. Now, this is important because when it comes to doing things like atomic models, when we look at the shell of an atom, that is why we talk about it as being the electron shell. It's not the electron ring. Sometimes we call them orbits, but even then, it's a spherical orbit because the electrons for the atom will be anywhere inside of that shell at any given time. And so this is why when we look at things like the double slit experiment, and we say we have a beam of photons inside of this, and we shine it at that double slit, what's the result? Some of them are going to go straight through. Some of them are going to come straight out the end, okay? Perfect model, they come right out the end. But some of them will be going this way. Yeah, they do call it a cloud sometimes, but we're moving away from that model. But anyway, some of these will be going this way. And see, they're all still inside. They're all still inside of this probability area. But they're all still coming out this area. They're all going different directions, and this is where the wave property comes in. Because we cannot lock down exactly where it is, we have to just make assumptions. We have to make guesses. And when they're all coming out of here together, just like those the particles in the ocean, they're all going in different directions. They're all interacting differently. And this is where the wave part of the wave-particle duality comes in. They're particles. They're acting like waves. A single particle is still just going to be a particle, okay? It's just one particle there, one particle there, one particle there, okay? There's lots of particles all over here. They're all doing the same thing, roughly. They're all moving. They're all moving according to their own design, though. And they're all acting like a wave. And we can prove this by just letting them interact with things and present themselves like any other wave. And this is the entire fundamental basis of wave-particle duality. So, is that any clearer for anybody else, or did I just waste an entire hour of everybody's time? I mean, I really hope it wasn't a waste. Because I tried really hard to explain this. And to be fair, it is a very abstract concept. It's a bit hard to grasp if you're not familiar with it. And I've already done this video 3 times now, trying to explain it. And I wasn't satisfied with my own explanation every single time. That's why I did this live and just committed to it. So, if you haven't understood it yet, then leave your questions down in the comments below, and I will do my best to explain it there. If you did understand it, leave your comments below and tell me I did a good job. Because, like, I could use the ego boost. My ego's not quite big enough yet. I cannot yet fill it with air and travel to Paris. I have to be able to balloon across the Atlantic Ocean on my own ego. Someday. Someday. But, either way, that's basically the end of this little lecture. I did enjoy doing this, though. This was fun. This was fun. I have more of these coming up in the future. And you're right. Flame, that is not a YouTube comment. Because that's a YouTube chat. I gotcha. I do have more of these planned. I think that I'm going to start doing this more regularly. I cannot guarantee that I will do one every Saturday, but Saturday is usually my day for doing these because it's like the only day out of my week that I have available for it. At this point, I'm now doing 7 days a week. I've got my normal gaming videos during the week. We will still have the live streams on Sunday. Tomorrow's stream is just going to be kind of a chill stream. We're going to sit and talk about tabletop games and all things that are interesting to us. In terms of other lectures, though, I want to do future lectures on other kind of socio-political things. I have two coming up. One of them is going to be on the slippery slope, both the fallacy and the proper application of it. I have one that is going to be on the objective concept of evil and the objective concept of good, just, by extension. I want to do more physics things. I want to discuss things like gravity, because gravity is another thing that is very poorly understood by most people, but is not terribly hard to understand. And anything else that you'd like to hear about. If you have any concepts that you would like me to break down, like if you have questions, okay? If you have questions, send me questions, and I will answer them. And yes, Flame, I do believe that evil can be objective as well as good. If you have questions, send me questions. Leave them in the comments. I would say send me something on Twitter, but I don't have Twitter, and I don't intend to download it either. I don't really have a whole lot of social media stuff, so comments are the way to go. And yes, Flame, bigger mass, bigger gravitational pull, but how does gravity work? And how does that, well, that was rude. Never mind, I'm not finishing answering you. You're mean. All right, I am going to get off of here, though. So, if you have questions for future lectures, just ask. If I know the answer, I will do a lecture on it. If I don't know the answer, then I'll just tell you I don't know. I mean, I don't know everything. I'm pretty smart. I know a lot of things, but I don't know everything. Yet. But that's going to be it for today. I want to thank everybody who came out. According to my my YouTube analytics, we had a peak of 4 concurrent viewers. I feel like we have more than that. I'm going to pretend we have more than that just because it makes me feel better. But yeah, this was a good stream. I enjoyed this. Don't forget to subscribe if you haven't done so already. I'm pretty sure everyone that I have now in chat is already subscribed, but, if you're new here, subscribe. Hit the bell icon so you get notified of whatever videos are coming. And I literally do a video every day of the week now, so I'm always here. If you know somebody else who also is struggling with this particular concept, with wave-particle duality, share this video with them. If it helps them understand it, then that's even better. And if they're still struggling with it, they can leave a comment down below and I will talk to them directly. Because that's the one wonderful thing about comments. I can address you. And that's fantastic. So, yeah, on that note, don't forget to leave a like on the stream if you haven't done so already. I know I did. Don't forget to leave a comment down below, and I will see some of you tomorrow. The rest of you I will see either next Saturday or whenever I get my next my next lecture done. And until then, well, take care.